Let me actually open the YouTube channel.
Hi, everyone, and welcome once again. Thank you for joining us today, where we're doing another webinar by Ancora Elements. We are going to delve into the topic of Gen AI, something that's very interesting and is all the rage these days. So, our topic for today would be unleashing the power of Gen AI, production-ready RAG systems. So, whether you're an AI enthusiast, data scientist, or just curious about the next big thing in technology, this session is for you. We have Rahul Agnihotri from Encora, who's a senior data scientist with us, and he's a tech enthusiast and always passionate about creating new Gen AI products. His hobbies would be biking, right? Biking, he loves to bike, exploring new places. And without wasting any more time, I'm going to hand the session over to Rahul, who will lead us and give us more insight into Gen AI and all its nuances. Thank you, Rahul.
Thanks, David. Hello, everyone. Welcome to this webinar. My name is Rahul Agnihotri. I work as a data scientist, and today we are going to learn about one of the use cases of GenAI, which are called the RAG systems. This is what we are going to learn. Now, I'll give you a little bit introduction to GenAI. Then we'll go dive into what RAG systems are, how we design RAG systems, and more specifically and more importantly, I would like to talk about the challenges in a RAG system. How do we evaluate the RAG pipeline? And we'll take one example scenario of what kind of data we can handle and how to use that data with our GenAI systems. So let's dive into a little bit of a description of GenAI. So GenAI, as the term says, generative AI is something which generates something. So under the hood, this is basically a machine learning model, a mathematical model, which takes some input and generates an output. Right? What it generates and what it takes depends on the architecture you're using. For example, we have architectures like GANs, we have variational autoencoders, and most recently, you must be hearing of models like GPT-4o, GPT Cloud 3.5 Sonnet, which are based out of the transformer-based architecture. What are the capabilities of GenAI? No, we can use these GenAI models to generate text. For example, you must have guys may have used the Chat GPT, which is basically a chatbot which generate text based on your input. It also has some capabilities with images. When you switch onto the Pro model of the Chat GPT, you can use again same. You can use use it for generating images. For example, there's a model called DALI or Midjourney. And you can also use the GenAI model to generate data itself. You can synthesize data, generate artificial data for your own uses. So this is a little bit of GenAI. I will dive into key terms of machine learning and generative AI as you proceed further. Now come the RAG system. So when you go into ChatGPT and you give any query to it, you get a response. But that response is based out of what that GenAI model, that LLM or that model has already seen in the past. But what if there's a question which is out of the context or out of the memory of GenAI? What if we found the answer to that? So there comes a picture of RAG. So what RAG enables is it adds external data to the GenAI's context, and your question can be answered using that data. So you enable your GenAI model to look into a data beyond what it has already seen in the past, and you can and it can answer your question based on that data. So if you expand the full form of RAG, it has three components: retrieval, augmented, and generation. Retrieval means you actually, based on a query, you fetch some relevant information, and then you augment it, which means you add it to the prompt context. I'll explain what prompt is. And generation, which is where the GenAI plays its role and it generates something. Here's an important term, which is prompt context. So every input you give to any GenAI model is called a prompt. And this input for ChatGPT would be a text. right? And this could take form of images or videos as well with more advanced models. Moving on, why do we need RAG? I've given a little bit of reasons why we need RAG. The basic application of RAG is to enable the users to get answers from the data which are out of the memory of GenAI's already learned data. So you have some external data and you enable the GenAI to look into that data. I know what this helps is avoid hallucinations. So let's say if you ask any question and if GenAI model doesn't know, if it is a well-trained model, you'll get a correct response. But if it isn't, then your model can hallucinate, or it can go with beyond a certain boundaries. With RAG, you can have a certain set of boundaries set already for the GenAI model, and you'll get the answer from that data. So you can avoid hallucinations, right? And you'll get comprehensive answers. And your data, which you can use, could be your own data. Even if it could be public or private, doesn't matter. Also, one more important use of RAG is why we need RAG is the data which generally GenAI models have been trained on are up to a particular date. And with RAG system, you can have up-to-date data which could be fed into GenAI's prompt context. What are the use cases? Some of the use cases of RAG would be, a document question answering system. So you have a bunch of PDFs or let's say text files, and you just want to chat with them. You can have your question answering system with them. You can use them as a conversational agents for your organization. You can use them for real-time commentary based on the real-time inputs that can always give real-time commentary. You can use them as assistants, like personalized assistant, I would say. It can be used for search as a hybrid search application. So you can build an application which could be used as a search engine and for knowledge management, again, with your local data. So how you prototype RAG? So designing a RAG system could be a little complex. The cloud providers like Google, Amazon, Azure have already built a lot of services and a lot of capabilities, which makes your life easy. But what if you don't want to use them, or you are not using any of their pipelines? Instead, you want to design everything from scratch. It is going to be difficult, and it needs a lot of knowledge and a lot of careful examination of each of the steps which are involved. So we'll look into these steps and understand what goes into RAG pipelines. So first stage is collection. Since RAG system are always depending on the data, the external data, you need to collect them. Now, it could be coming from any collection of files, any database, like connectors, and then you have to integrate them into your RAG pipeline. Now, parsing. Parsing is basically you have to whenever you collect data, you need to process them into a particular format, which could be given into which could be fed to into a GenAI system. Now, the parsing method you use depend on the models you're working with and your pipeline architecture. There's no set method for parsing. It depends on the data, and it also depends on the models which you're using. So there are two models basically involved in the pipeline. One is an embedding model, which we'll discuss, and one is the GenAI model itself. So depending on the combination of these two, your parsing method might change, and also on the input data type as well. For example, text will have different parsing methods, images may have different. The second important thing is chunking. Chunking is basically dividing your data into smaller subset, right? Why do we need chunking? Let's go dive into chunking maybe later, but for now, just remember that chunking is basically dividing your data into smaller parts, right? So you're creating subtext out of, let's say, a main text. Then comes the embedding part. Embedding is basically, so all the models like GenAI, not just GenAI model, all the mathematical models or the machine learning models basically do not understand text directly, do not understand images directly. As these are mathematical models, what they need is numbers. So what you need to do is basically transform your text or your image or your video into a numerical representation. And that's what embedding is called. So you basically create a numeric or an array or vector representation of your input data. We'll see how it looks like maybe a little bit into it. Now, when you have created those embeddings, you need to store them. For RAG pipelines, we call them as vector database because embeddings are nothing just vectors, and then you store it somewhere. We call it the vector database. You have to think about a lot of things like do I need any specific specialized vector database, or I can use my, let's say you have already your database in place in your company, and is it possible to use the same database, or do I need an existing? So there are a lot of things you need to think of or keep in your mind while designing this pipeline. So I have called this stage as setup, like collection, parsing, chunking, embedding, and storage, because these are like the pre-processing parts for your RAG pipeline. Now, during runtime, you have to think, take care of other aspects of the of complete application. One is the query. So query is basically the user input. So let's say you are building a chatbot similar to, let's say, ChatGPT, but it is a RAG application basically, which talks to your local application. Now you get in query. You need to think about how are we going to take that query and add it to the prompt context, and then basically going to send it. So you need to think about how are you going to pre-process it. Are you going to check it for grammar mistakes or things like that, because people can use any sort of query, right? So you need to think about how my query is going to look like for the model. Is there any pre-processing required or not? Second, now when you get a query, you need to do a search operation. So, and this search operation will be basically on the vector database. So you what you do is basically you take the query, you again, as I mentioned earlier, as you embed your input text, like the data which we have already chunked, you create that into a vector, into embedding form. The same thing you have to do with queries as well, because if these are English, you cannot use that English context. You need to convert it into a vector, again a numerical representation. Then what you do is basically do a search based on any search metric. For example, you can use cosine similarity or Euclidean distance, right? And then you fetch out certain relevant data related to the query. And then, so for one query, you search some vectors, or let's say some parts from the storage or from the vector database, and then you start, and then you you can give that as an input to the model. So this is one. And now, third part will be a conversation. Like, so you have one question, you get an answer, and then the user can give another question. Then you need to know how to handle that as well. So that is called conversation, like question answer, question answer. That is called conversation. I know. And then you need to have a specific layers and application layers and all set for all of these applications. And then comes the serving layer, because every model or every pipeline which you are going to design is going to be, let's say, used by folks in your organization or in your college maybe. So you need to know how to basically serve that, what kind of API you're going to use, like what kind of security layers you're going to add and stuff like that. We'll talk about maybe each one of these in little detail as we move ahead. Here we see is an example pipeline structure, how a RAG pipeline look like. I've taken one particular use case where I'm basically, my data is a MP4, a video, right? And what I'm doing is basically I'm taking that video, I am trying to fetch the audio out of it. Also, I'm doing an OCR. Basically, for example, if you consider this a webinar, I'm sharing my screen and I see a lot of data on the video as well. So I have my input data in format of my audio as I speak, and also the content which you see on the screen. So you have two types of content which you can utilize from this webinar as well. So let's say if you have take a video, example is webinar, you fetch the audio, you extract audio out of it, and you also extract these whatever text you see, and you collect everything and you and call it an extracted text. So let's say this is your method of inputting the text to the final model. You are using text instead of direct audio or direct video, and you create a database or your own local database which is your extracted text. Then what you need to do is basically you need to divide the chunk, need to divide this data into smaller chunks, and for each chunk you need to create embeddings and then store it. Let's take a pause here, and before moving ahead from the vector stores, um, you see I've divided my complete text into smaller chunks, and then I'm creating embeddings of each chunk separately. So I'll discuss what chunk is and why do we need it. So every model, every GenAI model, be it GPT-4o or Claude 3.5 Sonnet or any another model, when you give input, they accept the input of a fixed size, of a maximum size, right? And that size need to be known. Your text could be um, let's take it this way. Let's say there's a model GPT-4o, and it take let's say it can take only 100 words in one like as a in one in, as an input. It cannot go beyond 100 words. But let's say your input text is 1,000 words. So how will you handle it? So you need to divide that, and then you maybe you when you send the input to the model, you need to send only the 100 words only, which which can be handled by the model. So that's why we need to divide the complete text part or the data into smaller text chunks. And then when we get the queries based out of the query and the search operation which we are using, we fetch the most relevant ones, and only those parts. Let's say we have a query, and based on our search query, we only find that these two chunks are relevant to us. We'll fetch only these two chunks, and then we'll send that as a query, right? So that's why we need to divide into chunks. So when we have chunks, we create embeddings using some embedding model. Embedding model basically helps your data to get converted into a numeric representation. For example, I've given OpenAI embeddings model, which is, but this is one of the closed source model. You can use open source model from any open source library from Hugging Face. Um, so it depends. I mean, when you're building a pipeline, you need to experiment with all of these, whether you're going to use any closed source model like OpenAI embeddings, or is it possible to get better performance by using any open source models. So you need to take care of that as well. So when you create embeddings, you need to store it somewhere, which is basically a vector store. Here I'm giving you example of Pinecone, but it could be your other vector stores like files. This is based on the cloud, but files could be locally stored, ChromaDB, or you can use, for instance, let's say if your organization is already working with Postgres tables, you can use that as a vector store, and then you can use something like PG vector, of PG vector capability, and use the same search operations, which same functionality which a Pinecone any other paid source might do, right? Um, then what you do is basically you have your store, then you get a query from the user, you create the embeddings of that of the query, and then do the search operation and just fetch out the relevant vectors or the relevant embeddings or relevant chunks of documents, and then you rank them, basically align them in order of the relevancy of the query, and then this goes into the as an input to the model, for example GPT-4 or mini or something like that. Here, I'm just trying to illustrate what embeddings is, right? So there's an object one. This object one could be anything. It could be text. It could be an image. You have an embedding model. Embedding models are basically pre-trained on large chunks of data. For example, BERT, or Instruct embedding model. There are a lot of models available. So you need to use this embedding model. You can always create your own embeddings as well if you are working with like say if you use any libraries like TensorFlow or PyTorch, you can create your own embeddings model. But that's a tedious task. So, and you may never have that much data and time and compute capability to create a good enough capable embedding model. So you may well have used an existing embedding model. You just give your input to that embedding model, and you get a vector representation. And this is what you're going to store. All these arrays you're going to store in a vector database. This is a vector, and hence the name vector database. Now let's come up to what are the challenges. We have seen how can we design, what are the parts of it, and with each, we'll discuss each part of the RAG system as well as in form of the challenges. Right? We're not going to design anything here, but we're going to discuss is what kind of challenges we may come across and what could be a potential solutions to the challenges we see, and yeah. So there are three important stages to RAG system: data ingestion, retrieval, and generation. Let me go back to the setup this file. So the setup is something where you need to parse, basically collect your data, and retrieval also. And runtime is basically where you are going to generate something, right? So there are injection, there is retrieval. Data ingestion is basically coming from your on raw sources. Retrieval is dependent on the query. Oh, sorry. All these five labels you see are part of the data ingestion layer, and the retrieval and generation are part of the runtime layer. So retrieval will always be based on your query. Until and you have a query, you need not to retrieve anything. And generation is when you give some input to your GenAI model and you get an output. All right, we'll discuss each layers and what are the challenges and maybe possible solutions to it. Right. For the data ingestion is ingestion stage is it's a preparation or the first stage of the RAG pipeline. It's very similar. Let's say if you are designing a machine learning model and you take input, you do all your pre-processing, you do cleaning and removing noise and stuff. It's very similar to that. You collect your data, you pre-processing, and you store it somewhere. You create chunks sort of the data. You create the vectors, the embeddings of the chunks, and then you store these vector embeddings into chunks. So pretty straightforward. You collect the data, you create chunks of it, and create the vectors out of that data, and then store this vector into your vector database. Each step is very important, and the model which you're going to use and the size of the chunk you're going to use is dependent on the embedding model and the GenAI model as well. So we'll go to each part of it and discuss what could be the challenges and how we can handle those challenges. So let's say, let's come up with the first challenge, which is data extraction. Like data extraction is, basically parsing your data from your raw data structures. So let's say you have your text or let's say images or PDFs or any tables, any sort of data structure you have, you need to parse it or basically transform it into a more usable form. And this could be very challenging part. We'll look into one example, later, of what could be a potential challenge to parsing the complex data structures, right? Unstructured data is nothing, just as text, so it will have a different challenge or a different method of uh, extracting relevant information from that, or basically parsing it. Now, what can we do? Let's say, so we have PDFs, images, text, tables. Now, what could be challenged? And this could be very challenging. And what can we do, to make our life easier? Um, Already there are a lot of helpers for us. If you go online, you'll find a lot of solutions. Like for each specific data source, what could be the potential solution? For example, if you go for PDF, you need to know what is going to be the best uh, possible solution for passing data from the PDFs. Um, um, so you can use helpers like, for example, I've given a helper like called Llama Parse by Llama Index. So basically, this is going to help you with parsing complex documents like PDF and stuff. Second is chain of. I want to discuss this chain of table approach and mixed consistency, self-consistency tables. This are very closely related to the tables. Like many of our organizations have data in tabular form, and within the table, we can have text as well. So these two are very similar but different to each other. So let's consider you have you have a database and a lot of tables are there. What a chain of table approach will do is it will analyze your tables and fetch the relevant columns and rows based on the query. So it's just going to analyze the schema, write the SQL query, and fetch the relevant information out of it, and then you can process that. So um, then the second step is mix consistency table. This is going to analyze the data as well. So suppose you are working for an organization and it has a table which is basically, let's say, sentiment. If you go to Amazon, for example, if you go to Amazon, you go to a product and you see people comments by people, and let's say the relevant whether they like it or not, what kind of what they thought about the product is. So you may store that into your database as well. So what makes consistent table do is not just analyze. No, you get the relevant information out of the table, and then you can also analyze the the structure, basically the content of the table as well. And all this is going to help to basically extract relevant information from your databases. Right? I'm giving you a few examples. There are a lot of more solutions. Based on um, what kind of data source you have, your data extraction layers might change. Your methods might change. Right? Second challenge is what is the right chunk size and chunking strategy I'm going to use. As I told earlier, all of these models take input of a fixed size, of a maximum size. So for instance, let's say a GPT-4 model can take 128K words. For example, I'm using a word instead of a more technical term as an input. So you need to know what kind of model you're going to use, as a what kind of GenAI model you're going to use, and depending on that, your chunk size will matter, will change. Also, you need to think about if it is a conversational model, so not just one input, you need to think about the later inputs as well. So your chunking strategy or your chunk size will depend on what kind of embedding or the GenAI model you're going to use. Um, Defining chunking strategy, deciding how to partition the data into chunks requires scale focus depending on the use case. All right. Now, what could be our proposed solution? Like, it could be challenging, right? You need to know what is going to be our right chunk size, what is the chunking strategy we're going to use, and what. Now, let's look into the solutions, right? So, as I told you, there it depends on the two things: what kind of embedding model you're going to use, and also what kind of input or what kind of GenAI model you're going to use. Also, now it depends on also your architecture, like, or your since you are going to deploy this, it depends on a lot of other factors, like how much performant it needs to be. For example, let's go one by one. You can use always fine tune the model. So what it means is you take an embedding model and create embeddings of it. Maybe these embeddings are not relevant for your data. You fine tune it. Basically, you retrain the embedding model based on your own data and create the new embedding model. So this actually helps a lot because you already have a very high performance model, and you just fine tune it, improve a little bit more, and then create embeddings out of that. Uh, and then when you are basically dealing with the embedding model or fine tuning the embedding model, you have a lot of flexibility to play around what kind of uh, chunk sizes you can generate of it. Now, second is the use case, but again, so let's take for instance images and PDFs. So PDFs can have a lot of pages. So if you extract text out of it, you may have a large volume of text. Let's say you have 1,000 words. And if you're just having an image, for example, if you think about a degree certificate, right? It has, let's say, 100 words. You may want to have a different chunking strategy for these kind of data. Like depending on input, you may want to have different chunking strategy for, let's say, text-based PDF files, and maybe different for the images. Yeah. Right. Let's move on now from here. So I think it should be clear. We need right chunk size and chunking strategy, with basically depends on embedding models and your performance, like your performance pipelines. And then the third challenge would be how to create a or so any model or any pipeline you're going to create is going to be deployed. Let's say for your organization, for your or your college, maybe it should be robust. It should be scalable, and people can use it. It should not have delays or in responses, and it should not no it should not look heavy. So to create that pipeline, you need to have maybe. So let's say if you have a huge database and you have your vector database is huge, right? So maybe, for example, as if given billions of text images you're creating, it might be difficult to handle, just from one database. So what you need to do, you may have a distributed computing strategy, right? For different regions, you may have, a different strategies, and so you can basically create what's it the APIs which can handle this distributed data and basically handle the responses at a you know at a very high performance level. So maybe, and this is just since we are talking about data ingestion layer, so we're just talking from the data perspective, that you may have a distributed system. For example, your data is stored at various locations, and it's distributed across the system. And depending on your query, you retrieve whenever data from any system whenever required. So you don't have everything in one place, and you can and this way you can handle a large scale data store, and fetch the data at the right time and the right responses. Now, first layer is done, which is the data ingestion. Now let's come up to the retrieval layer. Retrieval is basically you have your input, which is a query from it's a user, and of all the data where embeddings which you have created and stored across, let's say, distributed systems, you need to fetch those relevant information. You're not going to input everything at once to the model, so you need to know which are the most relevant ones depending on my query, and you need to fetch those sub parts of the data from our system. This is what retrieval is. So I'll just read it out. Retrieval is a RAG in RAG involves the process of accessing and extracting information from the, like, say, external data source. It could be a database, document, knowledge graphs. If your retrieve data is correctly in the right format, then the answer generally will be correct. However, the effective retrieval could be pain. You can so that retrieval itself is a pain, and if our retrieval is not um, of good quality, we are not going to get the right good quality outputs. So let's talk about the challenges. Your retrieved data is not in the context. What is the context? Context, again, it depends on your query, on the query. So the query is your context. So a person is looking for an answer, and that's a context. You take this query and you try to find out. Let's say there are 100 different embeddings, and based on query, you want to fetch out this 10, right? For each input, it's going to be 10, and you use a certain metric to fetch those documents, or say, let's say, vectors. And let's say you're using cosine similarity. You fetch those 10. Now you're trying to analyze that if the relevant information, the relevant answer to that context is not in those in those 10 retrieved documents, you're never going to get the right output, right? So let's go point by point. You miss a top rank document. So maybe there was a top rank document. There was a document which had the right answer, but you actually completely missed you, and it is not even there in the 10 retrieved documents. You're not going to get the right answer. Or maybe the answer is distributed across the documents. So it's not there in one, maybe across multiple. And you, let's say, depending on your search strategy, you missed a few of them. That's what incorrect specificity is. So responses may not provide the precise information or adequately address the specific context of the user. So you actually miss some of the context. You don't have basically the right information or the complete information. So in first case, you may completely miss information while retrieving stage. In second case, you may partially miss information. And then there could be cases where you retrieve the information, but then you do something called re-ranking. I'll talk about re-ranking maybe later. And do re-ranking and completely jumble the whole context, and then maybe the input the model does not make sense, and so the model will never generate a correct output. So there could be, so you need to think about, like, what kind of search retrieval strategy you need to use, and if you're re-ranking, then what kind of re-ranking is it required, or is it actually required re-ranking or not? And if at all, what kind of re-ranking model you're going to use? Let's say, okay, I'll talk about re-ranking here. What can we do, right? Query augmentation. So let's say a user gives a query, but it's a very specific query, and maybe based on our vector search or embedding search, similarity search, we may never be able to find the right answers, or retrieve the right documents. So what you want to do is basically you kind of somehow change the query itself, or augment it with some predefined phrases or some predefined context. So the input query is always aligned to the inputs, making sure that the answers also is always delivered to the query, and never and the relevant documents while retrieving are never missed. So you always augment the query. You can always play around with this retrieval strategy. I mentioned, maybe let's say you are using some similarity metrics like cosine similarity or Euclidean distance. You can always play around with these retrieval strategies, and these may always help you to retrieve the right information. Hyperparameter tuning. I have mentioned a couple of hyperparameters here. What are actually hyperparameters? Let me talk about it. Hyperparameters are So if you guys have worked with, let's say, Python functions, when you write a function, you pass little parameters to it, like called the parametric functions. In case of models, we call them hyperparameters because we can tune them. We need to tune them. So chunk size is also one sort of hyperparameter, and the second is top K. So I was talking about 10 documents. What is this 10? This is the number of documents which you can retrieve at once based on the query. This can be changed. So that's what I've named similar top K documents. So you can always play around with, like, you, depending on what kind of chunk size and what kind of number your top K may change. You can retrieve 10, 15, or 20. You need to play around with this and see what could be the best chunk size or number of documents for your pipeline. And then comes re-ranking. What re-ranking is? Um, so let's say you have retrieved your based on your retrieval strategy, you have fetched 10 documents or 10 vectors. Like, just keep in mind, documents and vectors are the same thing. Documents are, uh, let's say, text, and embeddings are just numeric. I'll keep switching between these terms. So let's say you've retrieved 10 or documents or vectors, and this could be the ones which could be sent into the to the model. Now we can play around with these. Studies have shown that this could help. Like, play around these mean, so you have already these vectors in a in one alignment. You can change that alignment, and that's what re-ranking is. So you have one document, two document, and third document. You can shuffle these documents based on a re-ranking strategy. Um, One of the techniques is cohere re-ranking. You can always go and read about it. You basically just shuffle the retrieved documents or the vectors, and then you send it to the GenAI model. This could be helpful. This could always can also harm your application, because you are again changing the context. When I say context, I mean changing the meaning of the input. If you're playing around with the meaning of the input, it may be harmful for you. So you need to analyze whether re-ranking is going to help you or not. It may help or it may not. Always think, do test before you deploy any of your pipelines. Let's go to the second is your task-based retrieval. So when you deploy a pipe-based service, you need to be prepared of the wide range of users. You need to know what are your end users are, and that will depend on what kind of data you are extracting. So you need to know what kind of data you're going to handle, what is your target audience, and depending on these, your retrieval strategies may change. Like, you can have a different retrieval strategy for your images. You can have a different retrieval strategies for your text, and depends on what kind of driver users have and what kind of inputs you have. Um, and how going to handle this? Like, say you have one pipeline for everything, for all images, PDFs, and different resources. How we're going to handle it? So you can use something like query routing. So you analyze the query of the input, like the user first, and you need to analyze that, and then you decide what kind of retrieval strategy you're going to use. And then you reroute it to the data sources, or you can use it, reroute it to the retrieval method you're going to use. So I'll summarize a couple of challenges. So you need to let's move ahead, and then I'll probably summarize everything at once. Um, so we have talked about retrieval strategies, retrieval routing, and now text about the vector database from where we are going to retrieve the data. Vector database something is where you store your documents in vector format or embedding format, and this is where you're going to fetch your data from. Now, you can use any external vector database like Pinecone or VV8. You can have your local databases like Files or ChromaDB, or you can use your existing, these are specific vector database, or you can use your existing database if your company or your college or, let's say, organization is using. For example, I mentioned the name of Postgres. You can make use of Postgres as well. There's something called PG Vector, which almost does the same job. So you don't need any external data sources. You can always optimize your existing databases, and you can use that. So it will help you basically optimize cost and maybe the performance as well. Um, Depending on what kind of database you're using, your search method will change, right? Um, you may search the whole context, or you can take specific keywords out of that, and you can use something called a hybrid search, which takes in semantics and the keywords, in context. So you either you make use of hybrid search and play around with these methods and see what could be the right retrieval, a search strategy for the database which you are using. Um, Another thing, again, coming back to the chunking strategies. When you have large database, you need to find out again the chunk size and you to take, because large databases may have in answers anywhere, right? And um, what we have seen historically is that when the input size is large, and let's say if it's in the middle of the input sentences or an input prompt, the model tends to give a change in performance when look as compared to when it's in the beginning or the end, right? So how are you going to judge large data set could be challenge in itself. What are the no challenges, or what could be the approach of handling large data sets? I've mentioned quite a few. Creating document hierarchies. You align your documents. And you may create knowledge graphs. You create summaries of it, and you can create summaries of the documents, of large documents, and summarize it into smaller ones. And then you may have parent document retrieval, basically, which is you retrieve the summary, and then using the summary, you retrieve the parents. And there's something called Raptor or recursive retrieval. Recursive retrieval is something you retrieve more than once until you reach the um, right input, retrieve documents which you want to do. I want to discuss Raptor here. I'll give you an example what it is. So what Raptor is a method wherein you take a lot of documents, a large data set, and then what you do is you first is you're clustering. Clustering is basically combining the similar documents together. So let's say this document one and document two, and document one and two are very similar to each other as compared to three and four. So you combine these two, you cluster these documents, and then you create a summary of these documents. Again, you take document three and four, create a summary of those documents, and then you do it for all the documents, and then you do it once again, right? So this is something again goes into recursions. So you take the initial documents, you first create the cluster of it, you summarize them, then you take the summaries, and again you cluster and again summarize and do until you reach, let's say, a point where you think this could be a right number of, let's say, chunks I need, or let's say summaries I need. And then what you do is, instead of basically creating the embeddings of those documents, of the original documents, you may create the same embeddings of these, and your retrieval will be based on these summaries, and you need to keep everything all indexed. So when you basically retrieve the summary, let's say A as a relevant input for your GenAI model, you can retrieve summary one and two, and then you can go ahead and retrieve summary document two and three, the actual documents. The third is the generation part, which is basically where you have your input ready, and then you're going to give it to the GenAI model. What are the challenges here? One is memory is optimized. So always your pipeline has to be informant. Your query should not take long time to answer. So you need to optimize what kind of the response time for each user. Um, what's what are the strategy which you can use? Semantic caching is something where you always create the caches of the inputs and the outputs you are getting. So let's say you are in a conversation, you may cache it. You don't have to retrieve all the context again and again. You cache the inputs and outputs once, and then at time of the next input question, you can use this cache, and you can reduce the response time or the retrieval time, I would say. Where can we enhance this? There are two stages where we can improve the time of the retrieval of the overall response time. One is at the retrieval stage, and one of the calling of the LLM. Second challenge at the generation time will be inference cost. So while you're deciding which model you're going to use, will also impact the cost of the infrastructure. For instance, a more capable, a larger model, for example, GPT-4o is, let's say, it's always going to be more capable, but it may cost 10 times more than its, let's say, a next best model, which, let's say, example, GPT-4o mini. So you need to think about what is the cost of, of the LLM going to be while you design the pipeline. You will not always go ahead with the best model, but the model which is suitable for your application, and it gives the it works the best, and also the cost, the inference is not that much. So yeah, you select your model which, when I say minimum viable model, which means it does the job, but as the best cost. And also you need to think about, when you have decided the model, you need to know what are the how conservative, how can you um, well you deploy, so that you don't need to, basically the conservative use of the model. You don't call the model for everything. You can always have a system in place, um, where only the critical components of the pipeline are actually calling the LLM, and um, not every part of it. So take care of the cost and try to make the conservative use of the LLMs. The third is the data security. This is very important, and since you're using it for let's say for your own private data, it is very important to secure data, not just the organization or the college level, but also at the user level. So this can happen at two ways. So what you can do is you can have something called multi-tenancy, where you have keep your users' data separate, and so you ensure the data privacy and security for your each users, or a group of users, or let's say teams separately. And second thing is you can use Nemo guidelines. I think this is by NVIDIA. You can use these are not just the guidelines; these are the guardrails. And you can all, I think you can go to GitHub and see what are you can use this package as a tool, so that these guardrails are going to basically help you align the output, so that you don't uh, you get only the secure and the responsible outputs from the LLMs, and you never go off the rails. So these, and you can take care of these couple of things while you are handling the data security. You can use multi-tenancy. You can use some guardrails. Nemo guardrails is one of the examples I've shared here. Let's actually go back and look at what have we covered and the data ingestion. Okay, so there are three parts of the RAG framework: data ingestion layers, retrieval, and generation. Data ingestion, we saw a couple of challenges is, challenges can come at data collecting, how we parse the documents, how we handle the input. Um, then when you have the input, how you're going to parse it, how you're going to create the chunks, how you can create the embeddings of that, and how you're going to store it, and how scalable and robust your application is going to be, how you can use always a distributed system. Second stage was retrieval. So when you have your data store ready, how are you going to retrieve it? You can use different sort of strategies. You can use different side of retrieval strategies. You can tune your embedding models. You can use re-ranking, or you can augment your queries uh, as well. Depending on what kind of input it is, you can route your queries to to a specific kind of service. You can have different services, and you can route it to any specific retrieval services. Then we looked at, we can always optimize our vector database as well, and by looking into what kind of database we use and what kind of search application we use. Then the fourth challenge was the chunking of the large data set. Now you can create hierarchies, like document hierarchies. You can create graphs of the documents. So based so that everything is made, have a relationship, and we don't go into a huge ocean to search for things. Instead, you can use something like Raptor, where you condense your ocean into a small, let's say, river, and you search from there, and then you based on your indexing and your other Raptor building strategies, you can retrieve the relevant documents as well. Then we looked into what kind of challenges could come at the generation stage. It could be handling at the response time of the user based on it could be because of the how you handle your retrieval strategy, or how often you call LM, or what kind of LM you're using. So for instance, the larger model can take a lot of time to process the data, but is going to give the right output. Second thing is you can use a small model. It is going to take less time. The output might not be the best 100% of the times, but it will always optimize your cost. So you must take care of the what kind of model you're using, depending on what kind of inference cost you can infer, and how conservative you can use LLMs. Now comes the evaluation part. Let's say you build a pipeline. Now you want to evaluate it. Evaluation is basically testing your RAG pipeline. And for this, almost every time you need to have a test data in place. So you have your test data set. I will talk about it with example maybe later. But and you need to evaluate your RAG pipeline at every stage. So you can evaluate your in isolation. It means you can evaluate your retrieval pipelines and your generation, and you can evaluate your into enterprise to enterprise level as well, like end to end. Sorry. Um, what are the evaluation metrics we can use? So I'll talk about maybe recall and precision in a brief. So recall, so you retrieve certain number of documents, and now you want to measure certain metrics and and see how relevant it is. So you always need to have a data set ready, like evaluation data set ready for this. You must keep that. And because when you're talking about recall or precision, or let's say MMR or NDGC, you need to compare it with something. That's why you need a test data set. So for example, you have built a pipeline, you have your retrieval strategy, you have your embedding model ready, and you have created everything. Now you run the pipeline and you measure these metrics, which are, let's say, recall it, which measures how many relevant documents were retrieved within, like, whatever you have retrieved, how many are actually relevant. So you need to compare it with with something, and that something is coming from your test data. The second is precision. We basically compares the proportion of the retrieved documents uh, from the results you have already retrieved. So recall and precision could be a couple of metrics. Second metric which can take care of, think of, is something called MMR. It basically compares the top results. So it compares the rank of the top of the. So you suppose you have your data set and you have ranked for any sort of, let's say, input question. You have ranked a particular document with the best one. You compare the rank uh, of the document from the as against the retrieved documents. So based on your pipelines, you retrieve the document and see what is the rank of that document in your MMR, in your test data set, and you compare this at once, like how high the first relevant document is ranked in your retrieved results. So the first relevant document is basically a document from your test data set. So you just compare the best ones. NDGC is basically, it uses a different metric. It's called relevancy. Uh, so it kind of computes. It just not takes the first one. It takes all the relevant documents and see what kind of relevancy it has. It kind of you can use both of the NDGs, like both the metrics, MMR, NDGC, just to compare. Like maybe your first, like the highest ranked documents may have the answers. So it's always good to have MR in place, and also you need to know if it is not in the first one, it may be in some other relevant documents. So you can use something called NDGC. There are other metrics like Blue, Rouge, or Meteors. Basically, these all are related to information retrievals. These all metrics are basically from context of information retrieval. You can use Blue score or Rouge score or something called Meteor score, not just to assess how well the answers you're getting are basically compared to the data set you have prepared. Something called is called Bird score. So the Blue score, Rouge score, Meteor score basically are, in short, that they talk about what by matching the words and by matching the words. And Bird score basically talks about the semantics. Semantic is mean the meaning. So you can say a particular thing in two different ways, right? The sentence may take different form, but the semantic meaning, the actual meaning remains the same. So you can take some help of something called semantic score. I've taken an example of a BERT score. BERT is basically a model, and embedding model. You take that model and create and compare the embeddings of the two of the output from from your RAG pipeline and the output which you have already placed in your test data set, and you compare the similarity score between them. In general, it is called SEM score. If you take, let's say, a model like BERT, you can call it as a BERT score. And of course, you can take use of human evaluation. You can have a human team, and you can just check the how well the output generated from your pipeline is. There's a framework called Ragas, which you can go and look into it. It has its predefined functions, which kind of all gives a context expression score, a context recall score, and a couple of scores like faithfulness and answer relevancy. What faithfulness is, so let's say your question generates some factual output, right? And you just need to check whether that output is actually factually correct or not. So this faithfulness is going to give a score if the generated response from your RAG pipeline is factually correct or not. Now, that answer could be factually correct, but it may not be a relevant answer. So you want to keep another metric in place, which could be something called answer relevancy. So you can have all these in place, just to have a good look on what kind of metric work for you. And depending on these metrics, like context metrics, context recall, faithfulness, answer relevancy, or maybe if you're using these metrics, you need to change, you may need to change a lot of things in your pipeline. Every part of a pipeline may be need to be changed. I know, right from the parsing, chunking, what kind of embedding model you're going to use, what kind of retrieval strategy you're going to use, what kind of GenAI model you're going to use. Maybe everything might be tuned based on these, and that's why we need to have right evaluation metrics in place, right data set in place, which could be helpful for us. I didn't talk about parameters of GenAI. We'll keep it very short. So there are some parameters in GenAI as well. So it is not like you just send an input as text and everything is handled by GenAI. You there's a little flexibility in the output responses from the GenAI model as well, depending on some parameters like temperature, which kind of handles how varied the answer or responses it could be, or something called top P. We'll not talk about that topic. It's a little technical. So there are some parameters from the GenAI model itself. So you can read about it and you can tune that as well. Right. So before we go look into one example, let's just have a look into evaluation metric as again. You know, you can have recall all these information retrieval metrics and in place, recall, precision, MR, NDC. I've given you some examples. They could be more, and you can make use of the evaluation metrics, which could be useful for your use case. You can blue, rouge, semantic score, or human evaluation. This or you can make use of ragas and GVAL. So all this we have done is basically to make a robust pipeline, like all these evaluation metrics, all these challenges and how to handle them is just to make our pipeline robust so that when we finally deploy our solution, it generates the right output. It takes the response time is good enough, and it's basically under the boundary of our own data, right? It just did not hallucinate and just give the right responses based on the inputs from the user. Let's take one example. I mean, this is because data parsing is one of the most critical components of not just the GenAI or RAG pipeline. It's for any machine learning algorithm. Let's see if you're going to train. I'm just taking example of one. For example, let's say you're building a chatbot for shipment invoices for any shipment company, and you get what you get is invoices, and let's say there's a business person and he was want to know, what kind of uh, what were the shipment details, like for who was the seller and who what that shipment went to, like who was sold to, or what was the document number, how maybe what was the total price, or what was the number of units, what was the description, like any sort of question could be there, like a person can ask any question from this document. So you need to handle this. There could be multiple ways to it, right? I'm taking example of one invoice here. Now consider this as an image. This image could be like JPEG or PNG or any format, or this could come as a part of PDS as well, right? Now you extract this image. Now you have an image. Now consider you may send this image as an input to the model. Not this when I say input to the model, I'm just saying to the API. So you're going to use, let's say, OpenAI API, and you can always send it directly to the OpenAI. All the other processing is going to be handled by the OpenAI. But when you are sending this as an input, you need to take care of the model you are going to use. So right now we have a model like GPT-4o, which is capable of handling the images as well, uh, and text as well. And that's the name. That's why the name multi. That's why the name multimodal. So while multimodal is multiple modalities, that means it can take handle text inputs or image inputs, something like that, right? So they are in models which can handle these directly. So you can send in directly this image. Model may be able to handle this, depending on what kind of OCR strategies it internally involves. We don't know how have they built the model or handle the image, how they handle the images, right? But you can test. Maybe it works. If it works, it's great. But you need to check what kind of cost is going to incur. If it is, if it's something which we can take care for, if it's something which we can handle the cost, it's great. You can and if the response is right, uh, a pipeline will be very simple. It will not involve any pre-processing. You can just take an image, send it to the model, ask a question, and get the out response, right? Or second thing would be you process your own data because you are not going to want to use a heavier model, a bigger, more expensive model. You want to use a cheaper model which does the same job, but it is not capable of handling that images. You may want to extract the text out of, right? So the method of extracting the text of image is something called OCR, and you can make use of this OCR and extract text. Now this is not an easy job, right? A lot of pre-processing of the image may be required. Let's take an example. What kind of pre-processing methods we may want to use, and why do we need first of all this pre-processing? Because the image quality may differ, not just how the blurry they look or maybe the colors they have, how are they aligned. All these basically come as a part of pre-processing. So the better the quality of image, the better the OCR will be able to work on it and generate and extract the text. So if you somehow pre-process, your input image, the OCR will be able to better, and it's going to improve your extracted output, the accuracy of the extracted output. So you can use methods like binarizing, skew correction, denoising, scaling, rotation, cropping, and you can go ahead, please. I will always, encourage you to go ahead and read about these techniques. But we'll talk about one which is called layout analysis. It's called bounding boxes. So this is one strategy. What we are doing here right now is thinking of one strategy which we can use when we are building a text-based model. We are not using GPT-4, we are using a GPT-4 mini version, and we need to extract the text out of this OCR model. What could be the best? No, if you can use directly this image as an input to the OCR and you can get the output. But how can we improve? That's what we are learning, right? This is one of the strategies. It's called layout analysis, which basically defines the bounding boxes. So the image you currently see here is a raw input to the OCR. So you may not visualize this correctly, but no, but what you see here is the green boxes you see is how the OCR is looking at the image, right? It takes a smaller box, for example, like say, it takes this box, it sees it, and it extracts the text out of it, right? And it does it recursively. Like it will do it again and again, again and again, right? And it will like extract the text, but it doesn't know that for the OCR engine, this text and this text, it doesn't know whether it's separate or not. I mean, for the context of it, doesn't know it's separate or not. If it sees in the under the same box, it will extract and it'll put it to you. So you may want to somehow control it, and there comes a picture of layout analysis. So you create the bounding boxes beforehand before sending it to the OCR. So what you are doing is basically you are clipping sub images out of the main image, and then you are sending it to the OCR. So first you send just this part. So now the OCR is constrained to look into this only. So you extract text. So you know for sure all the text within this box now is extracted at one go. Second box will go and then it will be extracted again and again, right? This could be a nice strategy, right? I'm giving you one example. You can think of any other strategy as well, where you can take an image and apply all these corrections and all these pre-processing methods and extract text. All this is a lot of manual work. That's why I talked about when you're using services like from Google or Azure by Microsoft. or let's say Amazon, all of these helpers are already, like most of them are already in place. So they make our life easy. But if you're building something, everything from scratch, there are a lot of things you need to take care of. This in itself is a task, right? So, and this is just one stage of the whole rack system. So that's, I just wanted to show you one example of a data processing. This is it could be a real life use case. And yeah. All right, that's all I had, guys, today. Thank you so much. I hope you learned something. I know there are a lot of things which we may know of, and I will encourage to read about RAG pipelines, read about GenAI, different kind of models. This is a very interesting use case of the GenAI as a system, and it could be really helpful for you guys. I have tried to pick, the reason I pick challenges and all these proposed solutions, because something which you need to keep in your mind while you're designing a system, or you can always find examples, code examples and all online, but always keep in mind all these things when you're designing, and understand how complex it could be to design the whole RAG pipeline. Yeah, thank you so much, David. Do we have any questions? Hi, David, are you there? I think David is not able to respond. Probably stop my screen share for a second.
Yes, Rahul.
Yeah, David, do we have any questions here?
We don't have any questions for today. So if it
It's
will
okay.
go live, and then if questions come, we can add.
Yeah, sure.
So thanks, Rahul. Thanks
Thank
for
you.
the very insightful session.
Thank you so much, David. Thank you,
And
everyone.
thank you, everyone, for joining us.